Good morning, good afternoon, good evening, everyone. This is our team engine SPB. We are excited to share our project IoT Based Automatic Pressure Control for Biogas System. Over the past 10 days, we have developed a solution to make biogas pump control more efficient using IoT technology. Our agenda today covers 4 key points: what our IoT auto pump system is, why it's needed, how it works, and the process we follow to build it. We will wrap up by showing you the final outcome along with a demonstration video. What is IoT Auto Pump System? The IoT Auto Pump System allows users to control a biogas pump remotely, either through a physical button or a smartphone interface. The pump located 15 to 20 meters away can now be operated conveniently from the kitchen. Key feature of ISOLink. Our system is built around the ESP32, designed for the worker at Margo Tomo Resort. It combines a physical switch with a simple web interface, using the ESP protocol for reliable communication even at a distance.
Okay, first we can diagnose and define issues in Margo Utomo biogas system. As we can see, Margo Utomo operates a coal farm which is integral to their biogas production, and they're using biogas for the kitchen utilization. They produce biogas is fed into the kitchen via pipe connection and used for cooking. But the biogas system is pretty far away, and every time workers uses kitchen, they needed to switch the pump system, and the distance is around 20 meters away. And next, we can diagnose the problem definition. First, as we can see, the distance challenge, the switch is located 15 and 20 meters away from the kitchen. It is manual operation, and then pressure control itself needed, and efficiency improvement. The situation we get is pump switch needs to be done manually. Next, we define the problem factor, which is pump switch is too far from the kitchen, around 20 meter, and then switch system is an analog, and the worker has too much responsibility. And then we can define it as a 50%, 25%, and 25%. And we found the definition is pump switch has to be done manually because the switch is for an analog system.
For our item mechanism, our system starts with a user input either from a physical switch or an HTML interface. The ESP32 microcontroller processes this input and sends signal to the relay, which activates and deactivates the biogas pump, ensuring optimal pressure level. And next, the ESP32 acts as the core processor to manage data and control the data and the other hardware. The toggle switch allows manual override, while the relay responds to the ESP32 signal to control the pump operation.
I'll explain why the ESP32 is ideal for IoT-based systems. First, the ESP32 has built-in Wi-Fi and Bluetooth, which makes communication between devices simple and efficient. It also supports peer-to-peer communication, which allowing direct connections without Wi-Fi router. The ESP32's low power mode enhance energy efficiency, and its processing power and memory provide flexibility and scalability for various applications. With ESP Now, the ESP32 enables fast, direct data exchange between devices, extending the communication range. Our system uses two ESP32 ports for better control and reliability. Port A functions as a web server handling user input and sending signals to port B using ESP Now. Port B then controls the relay state based on the signals.
I will explain the code flow of board A in our IoT-based automatic pressure control system. Handle root function is set up the default web page for the web server, initializing the system to the off state. Handle on-off function is triggered when the user presses the on or off button, sending an HTML page to the server and updating the pump state. Button handling is check the count value to turn the pump on or off based on user input, responding to physical button presses. Signal transmission is when the state changes, the send data function sends a signal to board B, ensuring communication within the IoT system. The code ensures that the pump is controlled based on user input and the communication between boards is maintained for smooth system operation. In board B, the onDataReceive function handles signal reception via ESP-now. When this function receives a signal, it uses the digital write function to send a value to the relay module. If the received value is 1, it sets the relay module to high, which means the relay is activated.
The image above illustrates a core code snippet for board D in a control system. At the top, there is a function called dataReceive used to receive signal via ESP-now. The receive signal is processed by printing the source address of the sender using a for loop. Following this, there is a code block that controls the relay through the digital write command. If the value equals 1, the relay is activated by setting the relay pin to high, which turns on the solid state relay, and the pump will start with a delay of 1 second. Otherwise, the relay is deactivated by setting the relay pin to low, turning off the pump after the same delay. Next, the image illustrates the project making process for an IoT system, which includes both hardware wiring and programming the system. The first image on the left shows a microcontroller like an ESP32 or similar board connected via USB cable. The microcontroller is crucial for the IoT system as it handles communication, processing, and control tasks. The middle image depicts the coding phase, where the program is developed and tested on a computer. The code shown and the screen include the setup for receiving signal, controlling relays, and other operations essential for the IoT system functionally. The third image on the right displays the hardware setup, where various components such as microcontroller, sensors, relays, and connecting wires are laid out on a surface. The image shows the final product of the project, indicating the completion of the product making process. The hardware components are enclosed in a protective casing, which suggests that the system has been fully assembled and is ready for deployment. These enclosures likely house the microcontrollers and other electronic components necessary for the IoT system to function, providing protection and ensuring durability in its operational environment. The neatly arranged cable also suggests that the wiring and assembly have been complete, signifying that the project is now ready for testing and installation. Next, the image illustrates the process of accessing an ESP32 based IoT system via a smartphone website. The user connects their smartphone to the same Wi-Fi network as the IoT device, then uses the website to interact with the system. The ESP32 serving as the brain of the system facilitates communication between the physical device and the application. Through the app or web, the user can monitor and control various aspects of the biogas system, such as pressure. This process highlights the significant potential of IoT in automating tasks and enhancing efficiency. Conclusions. First, address the inefficiency of manual operating the biogas pump at Marco Utama. Second, we develop a wireless switch system using ESP32 module, allowing staff to control the pump directly from the kitchen. The solution improves operational efficiency and reduces the burden on workers. Third, the project highlights the importance of practical user-focused innovation that enhance sustainability and daily operation. Future improvements integrate sensors, and AI to automate the biogas pump, first using corrosion-resistant sensor and AI algorithm. Second, expected outcomes. The system will monitor gas levels and automatically control the pump, optimizing efficiency and reducing involvement. Third, AI algorithm predict usage patterns, improve maintenance scheduling, enhance sustainability in operation.